In this video, we're looking at dynamics, which ends up being a look at Newton's laws of motion. And we're really trying to explain why objects move. We've been talking a lot about how they move. And so mechanics, kind of the first of the two AP exams that this class prepares you for, is broken into two big pieces: kinematics, the description of how things move, and dynamics, explaining why they move the way they do. And dynamics we can break down further into Newton's laws, which is going to be our focus right now. And then the conservation laws, and that is kind of the other big piece. The conservation laws also move into other parts of physics, so we'll get there in a little bit. We're going to start by talking about the three of Newton's laws, or Newton's three laws, and then we'll look a little bit more specifically at the first and second. Before we do anything else, though, we need to define a force. A force is any kind of push or pull. The source of them could be you, but it could also be a lot of other things. Newton's first law is often described as the law of inertia, and the concept of inertia is fairly important when we're talking about both of Newton's first and second law. And then, there's a lot of ways this is said, but an object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by a net force. It's kind of the classic description. And so what we mean by a net force is that you add up all the forces acting on an object, the pushes and pulls, and you end up with no final sum. And if that is true, then there should be no acceleration. Newton's second law first law covers two situations, both moving and not moving, right? Because what's the difference between zero velocity and constant velocity? Well, the only real difference is your reference frame. The net force is zero, and we don't have an acceleration. And this leads to that statement of an object at rest stays at rest, an object in motion stays in motion. Newton's second law talks about when there is a net force, when there is acceleration. So if the net force doesn't add up to zero, then there will be an acceleration, and the acceleration rate will depend on that net force and the mass of the object. That's the fundamental idea. And although it's usually stated net force equals ma, if you want to think about what causes the acceleration, acceleration is equal to net force divided by mass. So big forces or big net forces cause big accelerations, and big masses cause small accelerations. So the first and second laws together cover all the possible motions or causes of motion for an individual object. If the net force is zero, it doesn't accelerate. If the net force is not zero, then it does accelerate or change its motion. So why is there a third law? The third law concerns itself not with the effects of an individual object, but the interaction, what we call action-reaction, pairs of forces between two objects. Usually stated for every action, there is an equal and opposite reaction. In physics, what we really mean there is for every force, there's an equal and opposite force. This explains what happens when two objects touch. It could be two ice skaters like this picture, or something else. And we will come back to this idea because it deserves its own time. An interesting piece that we've started to learn is that we can split apart motion in different directions, the x and the y of a projectile, for example. And it is also true that we can split apart the effects of forces in different dimensions. In the x direction and the y direction for a projectile, we have different laws of physics applying. Newton's first law applies in the x direction where there is no acceleration, so no net force. In the y direction, we have a net force of gravity causing us to have the acceleration due to gravity constant and down. You can solve problems using both and then combine them to get an answer about what happens in total. In order to do all of this, though, we need two new variables. We need to talk about the mass of an object, and we need to be able to talk about the force on an object. The mass is measured in kilograms. This is a scalar. It is not weight. Weight is a force. It's just another name of the force of gravity. Mass is intrinsic. It's built into the object. It has so much matter, and that matter has so much inertia or resistance to being accelerated. Kind of an extreme and fun example of this is if you were to take an elephant and a ping pong ball and let them float around in space. They're, quote, weightless. That's kind of a lie, but the effect is they're none the same, but they still have mass. And if you wanted to get that elephant to start moving and that ping pong ball to start moving, The elephant would still be hard to get to start moving. You need a lot more force to accelerate it at the same rate that would send the ping pong ball flying. So since a force is any kind of push or pull, it's helpful to think about the sources of those forces. Anytime two objects touch physically, obviously that would be a force. Anytime you go and touch something, that's a force. But they can be what is sometimes referred to as a spooky action at a distance. Gravity and the electric force, the magnetic force are all forces in this kind of range. Friction also behaves in ways that can be a little bit hard to understand initially because it doesn't seem to be exactly about physical contact. More on that later as well. So a force is a vector, meaning it has a direction, and we have to be careful about our vector math. It's equal to the mass times the acceleration. Because mass is a scalar, you can see that force and acceleration have the same direction in this equation. It is given the units of a Newton, named after Isaac Newton, and that unit is a kilogram times a meter per second squared. What that means is 1 Newton of force can cause 1 kilogram of mass to accelerate at a rate of 1 meter per second. So let's take a couple of examples here. If we're looking at the first law, an object is at rest. Any upward force must be balanced by a downward force. Those two 8 Newton forces opposed by a single 16 Newton force. If it's moving at a constant velocity, the net force is also 0. So 20 newtons to the right needs 20 newtons to the left. 60 newtons down needs 60 newtons up. This could be done even with forces at angles. Of course, you have to do a little bit more. You have to find the various components of those forces and then add them up. Right? We need 40 newtons up and 30 newtons to the right. Combine those together in a 3, 4, 5 right triangle gives you 50 newtons for force 3. Similarly, here we need 20 newtons down to counteract the upward components. And in this one, we've got to do this twice to find all the x and y components here. The x components cancel out, but force 3 needs 14 newtons. We can also talk about Newton's second law. And in Newton's second law, we are interested in what happens when there is a net force. So here we have an example. Alice and B are pushing on a crate. 100 newtons to the right, 85 newtons to the left. We could find the net force, which is about which is 15 newtons. And then we can apply Newton's second law, solving for the acceleration to find out that the acceleration rate of that 100 kilogram crate is 0.15 meters per second squared. There are actually 2 ways that we can go about solving Newton's second law problems. If you know the net force or can find it, then you can do a motion problem, a kinematics problem. So in this case, we've got 100 newtons to the right and 85 newtons up for a net force of 130 newtons at some angle. We can use Newton's second law to find the acceleration of the crate, 100 kilogram crate. That gives us 1.3 meters per second squared. And then we can use kinematics, if there's a constant acceleration, to find out that after 2 seconds, it has traveled 2.6 meters. That's starting with the force and finding the motion, but we can do the opposite. What if instead we have measured that the pushing has caused the crate to accelerate at 2 meters per second squared? Well, for that, we can use net force equals mass times acceleration to find the net force of 200 newtons. It's going to be at some angle. And we have one component there, the applied force from Alice pushing to the right, and the missing force is the force that B applies. And so we're going to use the Pythagorean theorem to find the missing side of that triangle, 170 newtons. What is the connection here? The connection between kinematics and dynamics is acceleration. If you can find acceleration either from a kinematics relationship or a dynamics relationship, you can then go to the other side. The important thing is to know that net force is, if it is constant, then the acceleration is constant, or vice versa. And then you can use your kinematics relationships. And I will close this by saying the big ideas here are the relationship between forces and acceleration, allowing you to then talk about the motion. The why of motion comes out of Newton's first and second law.